Hello students, we are going to talk about the decision tree and more precisely the classification and regression tree. Mm, the classification tree will be applied if your output is categorical, but if your output is quantitative, you would be applying the regression tree. So what is the decision tree model? What is it about? I'll just give you an insight about it and then we are going to understand it in more details later on. Okay. So what a decision tree does basically is that it's going to fit a simple model, all right, in different sets of rectangles. And what does this rectangle means? They are rectangles that will be formed by partitioning your feature space. Remember that the feature space represents your set of predictor variables, all right? So that's in a nutshell what it does. It might sound a little bit hard to understand what does this rectangle and everything mean, but we are going to come to that in a moment, don't worry. And however, for this course, there are different tree-based method, a tree-based model, and we will be basically considering only the card implementation, all right? There are others, like for example, the shade and these two, for example, but we are going to refer mainly to the card implementation of a tree, that is the classification and regression tree, which is a recursive partitioning method, binary recursive partitioning. So here we will see an example of a decision tree. All right. You will still not understand the concept of rectangles yet, but you will understand how this whole concept of fitting a model within a set of rectangles which partition the feature space relate to this decision tree that you are seeing here. But let's first try to understand what a decision tree look like and what it represents. We are taking this decision tree is based on the same example that we took last time, which is the iter's data, which you are used to by now. All right. And the idea of this decision tree is to predict the log salary of the baseball players based on different variables. But here we are going to be it's going to be based on the years at career and then the number of hits of the player. All right, these are normally the years in major leagues rather, and the number of hits of the player. So when you look at this decision tree, you will see that there are three values here. These three values, which are located at the end of a branch of a tree, all right, they represent what we call the terminal nodes. There are three terminal nodes in this example. I'm just giving you the definition, the notations and the idea behind a decision tree, and then you will be using these concepts later on. You will be coming across these concepts later on again and again. So just remember that all the values that are located at the end of a branch of a tree is what we refer to as the terminal node or the terminal leaves. Okay, and there are other nodes that you will see in the tree. This is, for example, an internal node. Why? Because why is it not a terminal node? It is not a terminal node because there are two branches that emanate from it. And if there are two branches that come from it, it means that we will refer to that as an internal node. And there is another internal node which is going to be referred to as the root node at times. All right, we refer to that as a root node at time. So what is the idea behind that? I'm going to give you the interpretation, which is relatively easy. It says here that if a baseball player has been spending less than 4.5 years in major leagues, then is less than means on this side, is log salary is predicted to be 5.11. However, if the baseball player has spent 4.5 years or more in major leagues, then his uh, predicted salary, log salary, will depend on what is the number of hits that the person did. If the person, if the baseball player has had less than 117.5 hits, and his number of years in major leagues is 4.5 years or more, then his predicted log salary would be 6. If the baseball player has spent 4.5 years or more in major leagues and the number of hits that he has done is greater than or equal to 117.5, his predicted log salary will be 6.74, which quite makes sense. All right, in this example, the more the number of hits, the higher the number of years in major league, obviously, the higher the salary. So that's a little bit the interpretation behind this decision tree, which is, as you would understand, very intuitive to understand. All right, very intuitive to understand. So what are we going to do next? We are going to have a look at the background, to have a brief background into the idea of a decision tree with certain notations and also with the concept of partitioning the feature space into rectangles. So that's what we are going to do now. What we are going to do is we are going to consider a regression problem to illustrate the principle of a decision tree, especially in the context of fitting models in a rectangle. So what we are going to do here is that we are going to split our um, feature space. We are going to assume that there are only two variables here for the purpose of illustration. Uh, then what is happening here is that when you look at this feature space, which there is one and there is another variable, you observe clearly that there are a set of rectangles that goes into uh, this feature space, all right? As we have been partitioning our feature space into different sets of rectangles. Now, what does this mean? First of all, let's try to see where is the feature space partitioned fully. You will see that it is partitioned fully only at two places, either x1 at the split point t1 or at the split point t3 for the variable x1. By the way, we refer to that as the split point, all right? At the split point t1 or the split point t3 for the variable x1. We will take it to be t1. We will start by t1, okay? We could have started by t3 as well. It is not a problem, but let's start by t1. So what is happening here? We understand that our feature space for our variable tx1 for values less than t1 can our feature our excuse me our variable x1 can be partitioned into two parts. One part for values less than x1 and one part for values greater than x1. All right, so that is what is happening here. We are partitioning the feature space into two parts. One for values that is less than t1 and one for values that is greater than t1. And these, when you look at it, you will see that you can consider it as a decision tree. Already you can see how it starts to form in a decision tree where you have x1 is less than t1 would be all thing. This branch will contain everything that relates to x1 is less than t1, and this branch will contain everything that relates to x1 is greater than t1. So remember that we start the um, by the split point, which fully partition the feature space. For example, T2 does not fully partition the feature space. because it stopped here. It doesn't continue up to there. So, for example, T4 does not do that because it stopped here, all right? It doesn't continue. And so this is why we always start by the one which fully partition the feature of the variable concern. Here, when we get for values less than T1, you will see now that there are two regions that you get from values less than T1. These two regions are based on the partition that you will make out of x2. You can divide x2 into two parts again, according to this example. One part is for values greater than T2 and one part for values less than T2. So in other words, you will understand that if x1 is less than T1, x2 can also be less than T2. And if it is less than T2 now, you will see that you will get one region which is R1. If it is greater than T2, you will get the region that is R2. That is a little bit how a decision tree is formed with regards to these rectangles that are partitioning the feature space. All right. And then if the value x1 is greater than T1, now there are two things that happen. If it is greater than T1, there is another split point here. So the other split point states that you can partition your feature space at T3 for values less than T3 but greater than T3 as well. But if it is less than T3, obviously you're talking about values greater than T1. So we can write here x1 is less than T3. If x1 is less than T3, if x1 is less than T3, does not mean all this. Does not mean all this. Because you have already set a condition here already. For values x1 is greater than T1 and x1 less than T3, right? For values of x1 greater than T1 but less than T3, in other words, this region is going to be considered as region 3. All right, it's going to be considered as region 3. And then for values greater than T3, now you partition the feature space at split point T4. Now, when you partition the feature space at a split point T4, it means that x2, remember that T4 relates to the vertical, x2 can be less than T4 or can be greater than T4. If x2 is less than T4, if x2 is less than T4, you will have region 4. And if x2 is greater than T4, you will have region 5. Remember, all these relate for values that are x1 is greater than T1. And not only x1 is greater than T1, but values x1 is greater than T3. All right. So this is how you get this decision tree. And what are these regions? These regions refers to the terminal nodes in your tree. You've got 5 terminal nodes. And what's going to happen? These regions will be fitted by a certain model. For example, a model can be a constant or it can be something else. But for example, if you're talking about the case of the baseball player, you remember that these regions were fitted by certain values, 5.11, which represented the log salary predicted. But what was the log salary predicted? It was the mean log salary for a certain particular region. In our example, here it was the mean salary for people who were spending less than 4.5 years in Major League. This was the value for people who were spending less than 4.5 years in a Major League. And this one is what? It's the average within the data set for values of years greater than 4.5 and values of it less than 117.5. So this is a constant that is being fitted into these different regions. There are 3 regions, 3 terminal nodes, and 3 constant being fitted, which in our example would probably represent the mean. So that's how now you understand the definition here. When I told you earlier that tree-based methods partition the feature space into a set of rectangles and then fit a simple model like a constant, for example, the mean in each of these rectangles. And these rectangles will represent the different regions, in other words, the different terminal nodes that you have. So that's a little bit about the decision tree. Now, all what you are seeing here can be represented mathematically now. All right, what you are seeing in this diagram can also be represented mathematically. So this is what I'm going to do next. What you saw here can be represented mathematically here. Let me just briefly show the different component of the equation. The M relates to the region, all right? Which region are you referring to? The first region, the second region, or you have 5 regions in all right? As you would see in this example, there are 5 regions in all. Then there is this part here, which refers to an indicator function. So x1 and x2 means what? It refers to the values at a certain split point. And x2 also refers to a value at a certain split point. For example, x1 t1, all right? You remember the example of x1 t1, and remember the example of x1 t2 being either less than a certain value or greater than a certain value, less than a certain value or greater than a certain value. So that's the indicator function. Now, what is happening here? You will have also this Cm, which represent the constant that I was mentioning, which has to be fitted into these different regions that you are going to consider. It says here that if a certain set of value is found within region Rm, you will take it as value 1. Otherwise, it will not be considered as value 1. It will be considered as 0. All right. Let's take one example. Okay. If a set of values is found in region 1, let's consider region 1. We will start by m is equal to 1. Okay. If a certain value is found in region 1, what's going to happen? If it is found in region 1, first of all, you understand that this would be C1 multiplied by the indicator function which will return either the value 1 or will return the value 0. These are the only 2 possible values that you will get from this part here. If a set of values is found within region 1, like for example, region 1 is what? Here, if a certain value is less than t1 and less than t2, if you have got in your data set, if you have x1 and you have x2 in your data set, and you've got 2 values here, and these 2 values, let's suppose they are less than t1. T1 is a number, and t2 is a number as well. So if your values is less than t1 and less than t2, it is supposed to be classified into region 1. So what would happen then? The indicator function will return 1. So what is going to happen is that C1 would be multiplied by 1. This thing turns out to be 1. But obviously you need to add with, remember, listen to me well, you need to understand that you have to apply that for the next few cases now. For region 2, will these sets of values, what we consider that is x1 is less than t1 and x2 is less than t2, will these be considered into region 2? Obviously, for any set of values that are less than t1 and x2 less than t2, will not be considered into region 2. It does not exist in region 2. You don't, excuse me, you don't have values x1 less than t1 and x2 less than t greater than less than t2 in region 2. That doesn't exist here. It is for x2 is greater than t2 that you have that. But when you are taking a set of values, the set of values stay constant, you don't change it for the different regions. So what is happening here? For the same set of values, this you would have your C2, a certain constant C2, multiplied by 0 because there is no, for x1 is less than t1 and x2 is less than t2, you will have, it is not located into region 2, which means that it does not belong to region 2, which means that it is going to be returning 0. Obviously, I think you would understand that for C3 would be multiplied by 0 as well, plus C4 multiplied by 0, plus C5, okay, plus C5 multiplied by 0. So in the end, what do you get? You get just C1, which is basically what we wanted. Our model is supposed to fit a constant here in this context. It will fit a constant C1 into region 1. And now, having understood it for region 1, you can consider another split point. Let's suppose you consider the other split point, x1 is greater than x2 is greater than t2, excuse me. If x1 is greater than t2 and x1 is less than t1, this does not belong to region 1 as you saw in the previous diagram. It does not belong to region 1 because now x1 is less than t1 and greater than t2 belongs to region 2. So it does not belong to region 1. So what is going to happen? It's going to be c1 multiplied by 0 this time plus, but it belongs to region 2. So it will be C2 multiplied by 1 plus, it does not belong to region 3, so it multiplied by 0, and it goes on. In the end, you will get only C2. So that is what is happening. You are fitting a model into these different regions. So here you would have C2, here you would have C1, C3, C3, C4, and C5 being fitted. And these C3, C4, C5, etc. was the predicted log salary, for example, in the previous, in the first example that you saw. So, and also you will need to understand that these different regions relate to the terminal nodes. So, for example, here in this example, we are referring to 5 terminal nodes based on the decision tree that I drawn earlier for you. So this is what I've drawn for you. I'm going to skip that. You already understood that. Now you can consider the same thing for a three-dimensional in a three-dimensional space. All right. If you consider here this example, you can look at it as a perspective plot of the prediction surface. So what is happening? What is happening here? Here you can see that x1 is here and x2 is here, but this vertical axis would basically represent the constant that is being fitted. You can have a look at the same thing that you saw in terms of rectangles now in a three-dimensional space where the constant is being fitted. For example, here you have the values of C3 equal to 0, for example, and you will see that for values of C3 for a certain value, for a certain split point, x1 is less than t1. You remember x1 is less than t1. This is what we are referring to. And x1 was less than x2 was less than t2. So this is the region that we are referring to. Less than t1, less than t2 was a constant of, a constant is being fitted. C1 is going to be fitted, all right? And C1 here would be in on the vertical axis would be -5, for example. It's just arbitrary values here to illustrate the concept. And you will see, for example, this relates to region 1 and C2 relates to region 2 here for values of x2 is greater than t2 but less than t1. This relates to region 2. So you can identify from a perspective plot as well the different regions just visually you can identify that there is a region here, there's a region here, another region here, all right, another one here, and another one here. So there are 5 regions in all right. And to understand these regions, you need to know what the split points are about. So there is a split point here, there's another split point here, there's another split point here on x2, another split point here on x2. Remember that these split points represent values. So here, these are arbitrary values that have been chosen just for your information to illustrate this concept here. You just need to remember that the vertical represent the constant being plotted. Obviously, the lower it goes, the smaller the value. The higher it goes, the higher the value. For example, C5 can easily be identified here because it is equal to 4. So you already understand that this is the 5th region. So we are going to have a look at the regression tree now. What we are going to do now is to learn how we can build a decision tree. So what we have done so far is to understand a little bit what a decision tree is from a general perspective. But now we are going to learn how we can draw a decision tree. But to be able to do so, let us define just quickly 2 things. And then, for example, we are going to describe in a decision tree, we will have a set of inputs, of P inputs. I think you are used to this notation, and a response, which is going to be a quantitative response for the time being, but the same thing applies for the categorical case. And then you will have the number of observations, which will be defined by I is equal to 1 up to n. So you'll have n cases in your data, and P variables, that is your feature space, consists of P variables. What the decision tree does is that it needs to automatically decide what the splitting variable and the split point will be, and then decide on the topology of the tree. So you remember that in the previous example I was telling you x1 was less than t1, things like that, x2 was greater than less than t2, and so on. In a normal setting, you would not have t1, but you would have a value here. This is supposed to be a value, and the x1 would represent something, obviously, and the t1 would represent a value for sure. And what I'm trying to say here is, how do you decide which one goes first? You might have a set of variables, x1, x2, etc. But how do you decide which one comes first? How would you decide which variable should be located here? Should be located, for example, at the start of a tree, because the tree will be built from here and it goes on and it goes on. But this year, for example, is less than 0.4. How do you get that? How come you have years less than 0.4? Why didn't you, for example, have its here? Why is year here? This is what we are going to explain. We need to decide on which variable, which splitting variable will come first, and which split point will be accompanied with that variable. That's the first step. All right, this is what I just mentioned here. All right, the first thing is that you need to find out the splitting variables, to decide on the splitting variables and the split points, because there are 2 things here: which variable goes first and what value are we going to consider. All right, for example, in the example that we took was years less than 4.5. How come we get that? Why is it here? Why is it 4.5? This is what we are going to explain. And then, after having decided on that, after having built our tree, because when you have come to understand how you will choose your split point and split variable, then you will get a whole decision tree, right? But the other thing that you will need to consider is the topology of the tree, which means that it's about the shape of the tree. Is the tree too big or is the tree too small? Things like that. Should we remove branches from the tree? Should we keep the tree as it is? This is what we refer to as the topology of a tree. Now, modeling the response. You remember I mentioned this to you. Excuse me. You remember I mentioned this to you, all right? You already understand what this represents, but here we are taking it in a general context. We are not referring to 5 particular regions. We are going to consider a model in a general context with M regions. So the same model applies as I explained to you earlier. Now the question is, what is this value? Okay, this value is going to be obtained normally by minimizing the sum of squares, which is something that you're used to, in fact. Okay, is by minimizing the sum of squared errors that you are used to. And by minimizing the sum of squared errors, where you have y, which represent your actual value, and f is your predicted value, f of xi, right? By minimizing the sum of squared errors, you come up to an average, which is the minimum. The average for the variable, for the output variable within the region Rm. Within the region Rm means what? Means for a certain value of x1 is less than a certain value, or for a certain value of x2 is less than a certain value. For a certain split point, x is less than a certain value, and certain split point, x2 is less than a certain value or greater than a certain value, whichever. All right. So when you will go in your data set, you will identify these different regions. You will have, let's suppose, x1, x2, and it goes on like that. We take only 2, for example, and you will see what are the values that you get there. These different values, if a certain value is less than, let's suppose, 10, and this one is less than 5, let's suppose, then it will be fitted in a particular region. Let's suppose we call it region 1. Then what you need to do is to look for all values that x1 is less than 10 and x2 is less than 5 within the data set, and then you will see what are the values of y corresponding to these. Let's suppose this was another one with that combination. There is another one here with that combination. There was only 3 combinations like that. Then what you would do is that you would take these 3 values and do their averages. By doing the averages, that's what it is here. By doing the averages, you get a constant fitted for that region 1 as if. Okay, so that's the principle behind. You're going to do an average of your output with respect to the regions concerned, with respect to the values of x within the region concerned. You're not doing an average on x, but you're doing an average on y with regards to the split point and split variables within a certain region. Okay, so that is the constant that is going to be fitted, as I explained, because it is the average that is going to minimize the sum of squared errors. But obviously things does not end there. There is more to come in terms of building a decision tree. Okay, here we go. So let's try to understand what's going on here. We will start by defining a partition. All right. How are we going to do so? We will start by determining a partition. Now we're going to determine that through a pair of half-planes. What is a pair of half-plane? Okay. To illustrate this idea, let's go to the example that we took here. For example, originally you would have a square like that. You would have x1 and you would have x2. Okay, if I decide to have to partition x1 to two parts, I've got two half planes. That is, I've got two regions that have been defined here. For a certain value, for x is less than a certain value, which I'm going to decide. And this value is what we will refer to as s in our example. All right? We'll define as s here. And if I decide to start by x1 as I've shown you, less than a certain value s, I've decided to start by x1, then j is referred to as 1. But if I decided not to partition by x1, but to partition by x2 completely, to define an half plane by x2, then for a certain value s, okay, then you would have j is equal to 2 for a certain value s that is being considered. So for you would have two regions, one for less than, for x2 is less than s, and one for x2 is greater than s, that is going to be region to be defined. So let's get back here. So this is what we are doing here. We are going to define a pair of half planes where R1JS represent the left side of the plane. Let's suppose I started by x1 to make things simple. Then it would mean that R1JS would be this region, and R1JS would be on this side, okay, where this is S here. So R1JS is defining all values of x for which xj, that is, let's suppose in our example here, x1, for which x1 is less than s, but I repeat, it's not necessarily 1. It can be any j, okay, any split variable. So basically, this represents the split variable, and this represents the split point. By defining that, then we can proceed, okay? To understand that, when we are going to build a decision tree, remember that the first thing that I have to decide is what variable come here first. From that, I will be able to continue with everything else. But the root node, what comes first? This is what I want to determine now. This is what I mean by building the decision tree. We will start by the root node first. But how do you get these values? For example, in the first example that we took, it was year less than 4.5. So how did we come up with the split variable year and the split point 4.5? How did we get to that? There is a procedure which is there, which determines that. Somehow this procedure determines that. Let me explain this procedure now. That will determine which variable will come first, okay? And if you look at this, well, you will have your y, let's take only this part, for example, and then we'll talk about, you will understand this one then. Let's talk about this part particularly. This is talking about a minimization, minimization of sum of squares with respect to a certain region, R2. This is what it means. You are going to minimize your sum of squares with respect to a certain region. When we talk about minimizing your sum of squares with respect to a certain region, it means that I need to find a certain value of C2 that will make this value, this sum, as small as possible. I will need to determine a value for C2 because this is what we are looking for, minimization with respect to C2. I want to minimize this sum of squares with respect to C2, which means that I need to find a value of C2 that will minimize this sum of squares. Of course, within region, within this half plane here, all right? So it's like as if let me just take a data set, this fictitious data set, to illustrate that. You have a x1 and you have x, let's suppose you have x1 only for the time being. You decided x1 to be the value. All right, you decided j is equal to 1 first. All right, what does this principle state? This principle state that you will need to look for all value of j is less than, j is equal to 1, for all variable j is equal to 1, that is x1, is less than a certain value s. Let's suppose it is 10. So you will need to look in your data set all values that you have, 15, 12, and then 9, and then 7, and then 11, for example, things like that. Okay, you have a certain input variable x1 which has got a set of values, and then you have a certain response y, which is let's suppose 20, 50, 15, 70, 40, and 30, things like that. So what does this principle states? This principle states basically that for this specific region x1 belongs to region 2 here, to half plane 2. What does half plane 2 means? Half plane 2 can be written as 2 j is equal to 1. If I took x1 as an example, j is equal to 1, and then s is equal to 10, because s is equal to 10 is a split point. 2 1 10 means what? All values of x1 less than 10, x1 is greater than 10, excuse me, because we are looking at the second, because remember that this is talking about values greater. So for x1 greater than 10, we are going to do the average of y. Okay, we are going to do the average of y minus a certain constant c2 that we are going to fit in the model. So we have like as if another column that you need to get a certain value for all values of x1, right, greater than or equal to 10, which means this value, this, and this. These four values of y, you will need to find a certain constant that you will fit in this model for these values. Oh Lord, excuse me. So you will need to find a certain constant that you would put here. Let's suppose it is 5, or it is 4. I don't know if it is 5. Let's suppose if it is 5, it's going to be a constant 5, for example, I suppose, and that you will need to fit in the model. But is 5 the appropriate value? What do I mean by is 5 the appropriate value to fit in within this region? It's going to be the appropriate value if when you take 20 minus 5 to the squared, plus 50 minus 5 to the squared, plus 15 minus 5 to the squared, etc., is the smallest possible value for any possible values of c. In other words, if we do that for 5, what kind of sum of squares do we get? If we do it for 10 now, what kind of sum of squares do we get? If we do it for, let's suppose, 7, what kind of sum of squares shall we get? So you understand that there are different possibilities for C to be considered. And it's going to be very difficult for us to imagine all the different possible values of C to fit, to compare with Y, all right, for this specific 4 regions, for these 4 specific values. So this is why we know that the appropriate value is supposed to be the average of these. So the fitting is going to be the average of these. The value that is going to minimize the sum of squares is going to be the average of these 4 values. Not the whole data set, but only the 4 values. 20 plus 50 plus 15 plus 30 divided by 4 will be our constant that will minimize the sum of squared errors for that particular region of 2, 1, 10, all right, or to 110. So this is just an illustration of what is going on here, all right. Now you have to understand that I've decided for x1. Now we need to do the same thing for another variable x2. That is, we'll have to do it for j2 and so on. So let's get back to this point here. Let's not diverge. You will see that this step is straightforward because there is a minimization that is going on, and the minimization is obtained by an average of y over that particular region. And this is an average of this C2 is obtained by an average of y. This C2 is obtained by an average of y over that particular region. This is what I mean here, all right? An average of y over that particular region. So this is an assumption that j is equal to 1 in this example, but you realize that you will need to do the same exercise now for another set of variables. J is equal to 2, and j is equal to 3, and j is equal to 4, and it goes on like this. Okay, so there are different things that you have to do here. Is that for a certain set of values, remember that the split point that I considered in the example was x is less than 10. Okay, s was 10, 2, 1, 10. Okay, so imagine the number of possible combinations that you have to go through. First of all, we've done it for 10, but you have to understand that we should decide whether this split point is correct or not. You have to do the same thing now for another split point, 15 for example, and you have to do it for another split point for the same variable and do it for another split point. So it becomes a very tedious process if you had to do it by hands, but fortunately the software will do everything for you. To finalize everything is that there has been a minimization that has happened for an half plane which is defined by a certain split variable and by a certain split point which you decide, for example. Then you will need to do a second minimization now, which is going to be based on the minimization of these two sum of squares, right? Because you will consider different combinations of j, because I have decided R2 110 or R1 110 means the less, all right, the side on the less one. For example, R210 is not less than 10, excuse me, it's greater than 10. I said it wrong earlier. It is greater than 10. R110 means x1 R1 110. This was yes, R2 110 means x1 is greater than 10. R1 110 means x1 is less than 10. For this one is greater than 10, for this one is less than 10, region 1. So we have decided a split variable j is equal to 1 and split point j and split point s is equal to 10. But you understand that there are different possible combinations. In a data set, you don't have only one variable. You will have several variables. Let's suppose you have 10 variables. You will have to repeat this procedure here. Forget this part here for a moment. But you will have to repeat this procedure like for 10 variables. But apart the 10 variables, you have different split points that you have to consider. 10 for one variable, another variable you have, for the same variable you have different possible split points. And what are you going to do? You are going to add what you got here, these two sum of squares for the different combinations of j and s. And when you have added the sum of squares for the different combination of j and s, you will need to look which one is the minimum. Was it for j is equal to 2, for example, and s is equal to 15? If it was for j is equal to 2 and s is equal to 15, that would mean if this was a minimum, because remember that you have different combinations that goes on. You have different combinations. You have to do it for j is equal to 1, j is equal to 2. J means the variable, yeah, the splitting variable. Imagine you have 10 variables in your feature space. So you have to do it for j is equal to 1 up to 10. Let's suppose, and then for each of these variables, you have different split points. S is equal to 1, 5, 2, all kind of split points. Let's suppose for j is equal to 2 and s is equal to 15, you got the minimum. You got the minimum of these two sum of squares. Then it means that the variable x2, all right, less than 15 comes on the first node, come at the first node. That is how you get to decide that. But obviously, this minimization process, you will not have to do it in by hands, but the software will do it for you. This is why things get easier now. This is the advantage of the this the advantage that we have nowadays, that we have computers that are able to solve such types of things for us. Okay, otherwise if we had to do it manually, it would have been very tricky to do so. So we will need to come up to number one, decide on j is equal to which variable will come first and which one will come as a split point. So this decision of a root node, for example, comes from this. And obviously, when you have come to this step of x2 is less than 15, x2 is greater than 15 here, the next step would be to repeat this procedure for all values of x2. Let's suppose you had x2 here, less than 15, and for all values less than 15, now your data set is reduced as if, right? You forget all the values that are greater than 15. You have a smaller data set. And the smaller data set means you will have to repeat the same thing that you've just done now, but with the smallest part of the data set, that is for all values of x2 less than 15. And for all values of x2 greater than 15, you will repeat that procedure here. And you will come up with a set of a certain split variable, all right, split variable, and a certain split point. Split variable j and certain split point that you will get for this and for this as well. Okay, so that is a little bit the idea behind building how you build the decision tree. All the building of a decision tree is based upon this principle here, the minimization of the sum of squares within two different regions and an overall minimization based on a combination of split variable and split point. Obviously, the advantage is that we have the inner minimization is done in a very straightforward manner. The inner minimization is done through the average, as I explained to you. So this already simplifies things a little bit. We don't need to worry too much about all the different possible values of C2 that we need to fix in there. So we can easily get the value of C2 just by taking the average. So this one is straightforward. Okay, and then you come up to the minimization with respect to the variables. So this is a little bit what I just explained to you right now. Okay, but the next step is how large should the tree be grown? All right, how large should the tree be grown? This is what we refer to as the topology of the tree, as I explained to you earlier. Because when you are applying this process, you might come up with a tree where you come up with, in the example that we took earlier, there were 3 terminal nodes with a small tree. But if you apply this principle here, this minimization principle, it will continue and continue the work. It's a recursive formula. Recursive means that's going to repeat itself for the different partitions, for the different branches. It will continue and repeat the procedure. In the end, if it may happen that I get a tree with 50 terminal nodes, not 3, but 50 terminal nodes. So the question that I need to ask myself now is a tree with 50 terminal nodes. If you imagine well, 50 terminal nodes, just remember what the terminal nodes refer to. 50 terminal nodes means what? It's going to be a very big tree with so many branches. The question that you want is a tree with 50 terminal nodes good or bad? If it is a very large tree, you will have overfitting, just like I explained to you in the concept of ridge regression. The more variables you have, the more you will have overfitting. And what does it mean? It means that when there is overfitting, your training set will be good in terms of its error rate, but your testing set will be very bad in terms of its error rate. And as you know, what we are interested in is not really the training, but the testing error. So then you can't have a too large tree. Obviously, you can't have a too small tree as well, because if you have too small tree, it doesn't capture the important structure within the data. It doesn't capture the pattern as well within the data, which means that it will not give you good prediction on the training as well, but it will not give you good prediction on the testing as well. So we need to come up with a certain decision on how big do we want the tree to be built. All right, and this is what we will refer to as the tree size. All right, the tree size, the topology of a tree. The tree size is a tuning parameter basically. It's a tuning parameter governing the model's complexity, and the optimal tree size should be adaptively chosen from the data. If you remember in ridge regression, we had a lambda that was used in our penalty term, all right, and the higher the value of lambda, the smaller would have been the coefficients. In other words, if we consider it for the lasso regression rather, the higher the value of lambda, the less variable we would have. The smaller the value of lambda, the more variables you will have. So if you have, uh, if you look at it carefully, the lambda was governing how many variables you wanted to in your model. But here you would have a tuning parameter that is going as well to determine, we are going to use as well to determine how far we want the tree to be grown. As an analogy, a bigger tree relates to a model like a lasso model with all the coefficients, all the variables with a non-zero coefficients. But a smaller tree would means what? A smaller tree is analogous to a lasso regression with a larger value of lambda such that you have fewer variables being considered. That is what a smaller tree is analogous to. So we want to find the right mix. How do we want? We don't want to have a too big tree. We don't want to have a too small tree. And how shall we decide on that? Okay, so this is what I'm going to explain in the next video. Okay, where we are going to talk about the tree size. Thank you for your attention for the time being. I will get to the next video and send you that for the tree size, where we will discuss about pruning and everything.